9q each, or 9 times the elementary charge, okay, if it's positive or negative. All right, so with that, okay, we can start talking about Coulomb's law. We said that Coulomb's law, this is the equation for Coulomb's law. The force of the electricity, or the electrical force between these two objects, any two objects, is K, which is the constant, okay, and it's given 9.0 times 10 to the negative 9, okay, newtons times meter square over Coulombs square, and this is given, okay, times the charge of the objects, which you have going to have two. Remember, we're looking at two objects, over the distance squared of the two objects, okay? So again, this is what this formula means. These are just examples, or just a little key to help, because sometimes they'll give you microcoulombs or nanocoulombs, and you got to be able to change them, okay? But this is Coulomb's law. This is the equation that we use, and Coulomb's law just says that the force between two charged objects equals the constant K times the charge of the first object times the charge of the second object over the distance squared that they're separated, okay? We know that the charge of if the charges of the objects go up, the forces go up, because they're directly proportional. If the distance of the objects go up, then the force goes down. If the distance goes down, then the force goes up, because they're inversely proportional. Make sure you feel comfortable looking at that, okay? Next, we're going to look at an example. Let's look at this example, okay? And we're just going to put two charges. One is 2q, the other one's 5q over a distance r. We're really not going to put numbers on that. But just by our equation of Coulomb's law, we know that the force equals 2 times 5, the two charges. Okay, we're going to multiply both charges, and we're going to put that over the distance. I didn't put k because it's a constant, but that would have to go in there, okay? And we know that the force between these two would actually be 10q squared over r squared. If you had the numbers, you would plug them in, and that's how you use Coulomb's law. And this is very basic, okay? Again, I didn't put k, but k would have to go in there, okay? All right, let's look at another problem. We have this problem right here. Okay, let me speed it up. Find the force between charges of a positive 0.0001 coulomb and a negative 0.0005 coulomb located 0.2 meters apart. Okay, so all the information is given. You know the equation that we're going to use for Coulomb's law, so we plug it in, right? So we're going to use, we're going to say that we put in all the numbers, and the force equals all these numbers multiplied divided by 0.2 squared, right? Because that's the distance. And when we do the math, we're going to end up with negative 112.5 newtons, and that negative, all it's telling you is the direction of the force, okay? That's all it's saying. Remember, force is a vector, so the negative on there tells you that it's going towards the negative charge, okay? But if they only ask you for the magnitude, then you could say that the force is 113 newtons. Because remember, magnitude is just the number. The direction is given by the negative or the positive charge, okay? So that was one example. The other example would be this one, okay? And it says two spheres have identical charges and are 0.75 meters apart. The force between them is 0.30 newtons. What is the charge on each sphere? Well, we know the equation that we're going to use is that one, so we can go ahead and plug in the numbers. We don't know the charge, right? So we can leave it as q squared, because the two spheres have identical charges. Okay, so if they're identical, we know that the q is going to be identical. We just got to square it, okay? Because remember, the equation is q1 times q2. And then once we do that, then we can square 0.75 and multiply it on both sides. And when we do that, okay, once we rewrite the equation, then that gives us this right here. It gives us 0.6875 equals, let's see, equals 9 times 10 to the 9th q squared, which is k times q squared. So in order to get rid of the k, we got to divide it on both sides. When we do that, then that gives us 1.875 times 10 to the negative 11. And in order to get rid of the square on the q, we have to square root it. So we do that, okay? And then that's going to give us q equals 4.3 times 10 to the negative 16 coulombs. Again, go through the math, It's just using the equation. Okay. Well, that's all we're doing. We're just using the equation. The next thing that we're going to look at is we're going to look at comparing objects. Okay. Proportions. You need to be able to look at proportions, and we already said that these equations are the equation that we use. Okay, force is directly proportional to the charge. So if it goes up, the force goes up. Same thing with the distance. If the distance goes down, then the force goes down. Okay, and we can see that from here. So if force 1 equals what it does, if force 1, okay, or there's two objects with identical charges, okay, then we know that force 1 would equal q squared over the distance that they're separated. But what if, okay, those two objects, if the charge on those two objects was doubled, okay, and that's what I did here. So the second force, or the other force, would be 2 times the charge of the objects over the distance, right? So don't forget to square. So we go ahead and square that. So that gives us 4q squared over r squared, okay? We know that q squared over r squared is equals the first force, so that would give us 4 times the first force, okay? Again, that's just doubling the charge. We know that the force will go up, and it goes up 4 times the original force. You gotta be able to look at these problems and find how those two forces compare. Okay, so let's look at another problem. Okay, it's gonna be the same thing. We're gonna have object 1, object 2. We know that what the forces are, but the first object is gonna be the original one again. Okay, force 1 equals whatever charge it has times the distance over the distance squared, right? And the charges are identical. All these problems have identical charges, right? But on the second problem, or the comparison, the second object, you actually have, the distance has been quadruple, right? And you can see that 4 times the distance. Okay, so that means if the distance goes up, we know that the force has to go down. So when you do the math, okay, we know that q squared is going to stay the same because it didn't change, but the distance, right? When we square 4 times 4 is 16. We got to square r. We don't know it, but it would equal 16r squared. And when we compare that to the first force, that gives us 1/16 of the original force, or force 1. Or it just tells us that is force 1 divided by 16, which is the same thing. Okay, so that's when you quadruple the distance. Now, let's do something else. What if you quadruple the force? Let me go back, so at least to where we're going to show this. So what if you have this original charge, right, this force, and all you're doing is the charges are the same, the distance, they're separated over a distance, but now what you're going to do is you're going to quadruple the charge of the objects, and you're going to use only a third of the distance, right? So what that's going to do, one, the Q, since you're quadrupling the charge, then that means the force goes up. And if the distance is decreasing, that means the force is going to go up as well. So that's a double increase of the force. So that means that 4 squared is 16q squared. Okay, if you do the math, then that's what you get. And then you got to divide 16 by 1/9. So what that gives you is 144 times the original force. Okay, and that's what what it does when you use only a third of the distance and you increase the charge. Okay, and again, that has to do with proportions. Guys, I hope this helped. Look at your other problems. I tried to go as fast as I could. It took us 15 minutes, but I hope it helps, and I hope it clarifies and it brings back everything we learned about electrostatics. Okay, have a good one.